All right, today we're going to tackle a topic that is just absolutely critical for anyone writing Python, especially when you get into data structures and algorithms. We're talking about the big battle, dynamic versus static typing. It's the very thing that gives Python its greatest strengths, but it's also the source of some of its sneakiest, most frustrating bugs.
Okay, so let's just jump right in with a little challenge. Have a look at the code on the screen. It's a super simple Python function, right? It's just supposed to find the maximum value in a list. So take a second. Can you spot the bug? I mean, on the surface, it looks totally fine, doesn't it? So if you look at that first call, the one with a nice, clean list of integers, yeah, that works perfectly. It returns 8, no surprises at all. But that second call? Ooh, boy, that's a ticking time bomb. It looks almost the same, but we've sneakily swapped one of the numbers for a string. And here's the crazy part. When you run this, Python gives you 0 warning until it's way too late. The whole program just crashes right in the middle of execution with a type error. This is that hidden danger we're going to unpack today.
So that crash, that's not just a random error. It actually points to a really fundamental difference in how programming languages handle data types. It all boils down to one critical question. When does the language actually check the types? Does it happen before you run the code or during the run?
Well, Python is what we call a dynamically typed language. And the easiest way to think about it is this. Imagine a Python variable is just a general purpose box. You can toss an integer in there, and then later you can take it out and put a string in instead, and then a list. Python really doesn't care. It only bothers to look inside that box at the very last second, right when you try to do something with the value. And that's what we mean when we say it checks the type at runtime. And this slide really shows you what that means in practice. Look at the Python code on the left. We have a variable x, we make it 10, then we turn around and make it hello. No problem, Python's totally cool with it. But now, look at the Java code on the right. This is a statically typed language. You declare x as an integer. The moment you try to assign a string to it, bam, a compile error. Your program won't even run. See, in static typing, the rules are set in stone before the starting gun ever fires.
Now, you might be thinking this dynamic thing sounds kinda dangerous, right? But it's not a mistake. It was a very deliberate design choice for Python. But it's a classic double-edged sword. On one hand, it gives you this incredible, amazing power and flexibility. But on the other, yeah, it can be pretty perilous. Okay, let's talk about the good side first, the power. What you're seeing here is something that would make most statically typed languages just break. We've got a single list, our mystack, and we're just throwing everything into it. An integer, a string, another list, even a whole dictionary. This right here, this is Python's superpower. The ability to create these incredibly flexible mixed type data structures like it's no big deal. But of course, with great power comes, well, the dark side. Take a standard binary search. In this first example, what happens if you accidentally search for the string 7 in a list of numbers? The program doesn't crash. Nope, it just quietly tells you false, that the number isn't there. And that is a terrifyingly subtle bug. But it gets worse. Look at the second example. If your list has mixed types in it, the whole thing just blows up mid-search with a type error. This is the kind of runtime terror we're talking about. And this flexibility, it isn't free. It comes with a hidden cost. And that cost is memory. Get this. A single integer in Python can use up to 7 times more memory than the exact same integer in a language like C++. So why? Well, it's because every single object in Python is carrying around this extra baggage. It has to keep track of its own type, its reference count, all this extra info just so it can be dynamic. You really start to see this performance hit when you do something like, say, summing a million numbers. C++ just blazes through it. Why? Because it knows from the start, hey, these are all just numbers, let's go. Python, on the other hand, has to be way more cautious. For every single addition, it has to stop and ask, okay, is this a number? And is this a number? Okay, good, now I can add them. That constant checking over and over again really adds up and makes it a lot slower for these kinds of heavy lifting tasks. So after all that, you might be thinking, okay, so Python is just not for serious, robust code, right? No, absolutely not. The thing is, modern Python has evolved. It's given us some really powerful tools to handle these exact risks. We can actually get the safety of static typing without giving up that flexibility that makes Python, well, Python.
Okay, check this out. This is our same binary search function from before, but we've given it a modern upgrade. We've added what are called type hints. See how we're now explicitly saying that the array parameter is supposed to be a list of ints and the target is an int? Now here's a key point. Python itself doesn't actually enforce this when you run the code, but these hints are like a super-powered form of documentation, both for other developers and, more importantly, for the tools we're about to talk about.
And this is the tool that brings it all together, mypy. Think of it as a static type checker for Python. It goes through your code, reads all those beautiful type hints we just added, and finds any type mismatches before you even run your program. It basically acts like a pre-flight check or a compiler for your Python code. This is how you find those potential disasters before they ever have a chance to blow up at runtime.
All right, let's tie this all together. How do you take all these ideas and actually use them to write professional, production-ready Python code that's both flexible and safe?
Here's your 4-step playbook for writing solid, modern Python. Number 1, use type hints everywhere. Seriously, for all your function signatures, for your important variables, think of it as your first line of defense. Number 2, run a static checker like mypy. Make it part of your regular workflow. Catch those errors before they can cause trouble. Number 3, don't just rely on the hints. For really critical code, especially stuff that gets data from the outside world, you should explicitly check your inputs at runtime. And finally, number 4, and this one is so important, none of this is a substitute for writing good, thorough tests. You still need them. So in the end, it's all about trade-offs, right? This table really sums it up. Dynamic typing gives you that lightning-fast prototyping and amazing flexibility that we all love Python for. And static typing, well, that gives you the bulletproof safety and raw performance you get from languages like Java or C++. You know, the mark of a great developer isn't just picking a side, it's understanding the trade-offs, knowing what a specific task requires, and then using the modern Python toolkit to get the best of both worlds.
And you know what? This whole conversation really brings us back to one of the core ideas from the Zen of Python. Errors should never pass silently. That silent bug we saw in our binary search, that's exactly what this is talking about. So when we use things like type hints and mypy, we're not fighting against Python's nature. We're actually leaning into its core philosophy. So the real takeaway here isn't about whether dynamic typing is good or bad. The real question is, how are you going to use this incredible power responsibly in your next project?